We're going to take a look at acids and bases and then introduce organic compounds. All organisms require water, and if you remember, water is a polar molecule. So it has partial positive and partial negative charges because it's got polar covalent bonds between the hydrogen and oxygen molecules. And so it's going to form hydrogen bonds between the partial positive and partial negative charges between two polar molecules. So this is going to make water a very good solvent. So it's very good at dissolving things. And so very good to know which of the following is able to dissolve in water. So a good way to think about this is which of these would be hydrophilic. So hydrophilic just means it likes to mix with water and dissolve in water. So if you have a non-polar molecule, and that would be something like oxygen, carbon dioxide, any of the lipids, they have non-polar covalent bonds, and so they're going to be sharing their electrons equally. So there's not going to be any partial charges on a nonpolar molecule, so they're not going to be attracted and form any hydrogen bonds with the water. So they're going to be hydrophobic. And so they are not going to want to mix with the water. And a good way to think about this is if you have something like salad dressing, which has a lot of oil in it, and you pour that into some water, they do not mix well. Okay, if you have polar molecules, so maybe you have something like glucose or proteins, they have polar covalent bonds in them, and so they will have partial positive and partial negative charges. Because they have polar covalent bonds, they're going to be sharing the electrons unequally. And so because they've got those partial positive and partial negative charges, they will be attracted to the partial positive and negative charges on the water, and they will form some hydrogen bonds with the water molecules. And so these polar molecules are hydrophilic. And so they will dissolve in the water. And a good way to think about this is if you think about sugar, or if you think about like glucose, that dissolves very well in water. Okay, so it's hydrophilic. Okay, salts or ions. So if you think about like sodium chloride, a salt, so that has a full charge. So you'd have these ionic bonds holding together the sodium and the chloride ion. The opposite charges would attract each other. But when you throw the sodium chloride into water, the water is very attracted to the full charges on the sodium and the chloride ions. And so they will surround them and separate them and dissolve that ionic bond. And so the salt will dissolve in the water. So the ions will be hydrophilic, and they will also mix very well with the water. Okay, so that would be good to remember which ones are hydrophobic and which ones are hydrophilic. Okay, next we have acids and bases. So make sure you know the definition of an acid. So acids are going to release hydrogen ions into a solution. So if you throw an acid into water, it will fall apart. So if we have like hydrochloric acid, for example, and you throw that into water, it releases hydrogen ions. And so that will increase the hydrogen ion concentration of the solution. And if you have something like carbonic acid, and you throw that into the water, it also will release the hydrogen ions and increase the hydrogen ions of the solution. So just remember that acids will release or donate the hydrogen ions in the solution when you throw it into the water. So acids will end up increasing the hydrogen ion concentration. Okay, and then I'd also know the definition of a base. So remember that bases are going to accept or remove the hydrogen ions from a solution. So when you put something like ammonia into water, it will combine with the hydrogen ions that are in the water. And then over here on the other side, you end up with an ammonia ion, and notice that the hydrogen ions are gone. So the hydrogen ions get removed, and so that'll decrease the hydrogen ion concentration of the solution and make it more basic. And then we also have another base. This is sodium hydroxide. And when you throw it into water, it separates into a sodium and hydroxide ion. But then the hydroxide ion that's been released will combine with the hydrogen ions in the water. And then we end up over here with a water molecule. And notice that the hydrogen ions are now gone, so they've been removed. So just remember that bases are going to remove the hydrogen ions from the solution, and that'll decrease the hydrogen ions and make the solution more basic or alkaline. Right, and then pH. All we're going to be measuring in pH is the hydrogen ion concentration of a solution. And that's why there's a big H in pH. Okay, so that'll help you remember that we're just measuring the hydrogen ion concentration. And so you can see with the formula for pH, we're just measuring the negative log of the hydrogen ion concentration. Okay. So when you calculate the pH, and I'm not going to make you do any calculations, but to figure out the pH, when you do the negative log at the hydrogen ion concentration, because it's a log that you're doing, you just take the exponent here and get rid of the minus sign, because these minus signs will cancel each other out. And so just whatever this exponent is, that's going to be your pH number. Okay, but I won't make you do any calculations for pH. Okay, remember the pH scale ranges from 0 to 14. And a pH of 7 right in the middle is neutral. So there's an equal amount of hydrogen ions to hydroxide ions, and we'll see that in pure water. But if you have a pH number that is less than 7, that means that you've got more hydrogen ions, and that would be acidic. And if your pH number is greater than 7, that means you have less hydrogen ions, and that means that your solution is basic or alkaline. Okay, so just knowing that pH scale and just knowing what those numbers mean, that's all you need to know there. Right, and then here's just a picture of the pH scale. We've got a pH of 7 in the middle, neutral. Hydrogen ions equal the hydroxide ions, but if the pH number is less than 7, that means you have more hydrogen ions, you're going to be acidic. And if your pH number is greater than 7, that means you have less hydrogen ions and you're going to be basic or alkaline. And because the pH scale is a log scale, that just means that anytime that you increase or decrease a number here, like if you're going from a pH of 4 to a pH of 5, it just means you have a tenfold difference. So for example, a pH of 4 is going to be 10 times more acidic than a pH of 5. All right, and then just to introduce organic molecules. Organisms are made up of mostly 4 elements, which are hydrogen, oxygen, nitrogen, and carbon. And so the way I remember that is HONC with a C, not a K. Okay, so if you remember HONC with a C, those are the 4 elements that make up most of organisms. Okay, so carbon is pretty important. And organic compounds are going to contain both carbon and hydrogen. And so we've got 4 different types of organic compounds. We've got carbohydrates, lipids, proteins, and nucleic acids. And then the inorganic compounds, they may have carbon in them, but they also don't have hydrogen. So for example, carbon dioxide would be an example there. It does have carbon, but it doesn't also have hydrogen in it. And then other inorganic compounds would be things like water and oxygen, salts like sodium chloride, acids, bases. Those also would be inorganic compounds. Okay, these 2 words are good to know. A monomer. So mono just means one and mer means part. So a monomer is just a subunit or a building block of a polymer. And poly meaning many, and mer means part. And a polymer is just many monomers that are joined together by covalent bonds. So I've got listed over here 3 of the polymers. And let's just put down the monomers that they're made up of. So for carbohydrates, the monomer or subunit or building block that the carbohydrates are made up of would be the monosaccharides. Okay, and proteins, that would be the polymer, and the monomer, the subunit or building block of the protein, would be the amino acids. And then nucleic acids would be the polymer. And to make a nucleic acid, we would just join together a bunch of nucleotides. That would be our monomer. Okay, we've got 2 different types of chemical reactions. We've got our dehydration synthesis reactions. So these are going to be used to synthesize or make the polymers. And if you just look at the name, dehydration synthesis, so dehydration, we're just going to be removing a water molecule to make the polymer. And then we're going to break down the polymer by doing a hydrolysis reaction. So lysis to break apart, and we're just going to add water to do that. So here's an example of a dehydration synthesis reaction. We've got a polymer that we've started, and we're just going to make it longer by adding a monomer to it. So we're going to do our dehydration synthesis reaction here. So we're just going to remove a water molecule and then make a covalent bond and join that monomer to the rest of the polymer. And there would be an enzyme here to catalyze that reaction. Okay, and then to break down the polymer, we would do a hydrolysis reaction. So we've got our polymer up here on top. And then here we've added a water molecule, and there would be an enzyme involved to catalyze this reaction. And then here you can see we've broken off one of the monomers, and then here's the rest of our polymer on the left. Okay, and then going to the right, we're going to do a dehydration synthesis reaction. We've got 2 monomers that we're going to squeeze out a water molecule and form a covalent bond and join the 2 monomers together. And here we're going to make a dimer. We've just got 2 monomers together. And we've got one enzyme doing that reaction. And then if we go the reverse direction and go back to the left, we can do a hydrolysis reaction and break the dimer apart back into the 2 monomers and do this hydrolysis reaction. So we would add the water molecule with the help of the enzyme and break those monomers apart and separate them and add our water molecule in there.